Hello, everybody. Welcome to the Module 1 Topic 1 Review. All you will need for the next, 30 minutes or so is your review packet. It looks kind of like what I'm doing here, but it's got two sides. It's got a bunch of problems on this side and then a bunch of problems on this side. I'm going to walk through the entirety of the left-hand side today. It is your job then to take this information, use what you know, and do the practice examples on the right-hand side. We won't use a calculator today. All we're going to need is our brain, our pencil, and maybe some notes if we need. But I think I'm going to be okay. I'm okay if you're okay. All right, ready? Let's start. Feel free if you have a specific question you want to use to look for the timestamps in the description, or if you're on YouTube, the little slider bar on the bottom is going to have some breaks in it as well. But without further ado, let's just go ahead and head into question number 1. And this is going to take us right back to nearly the first week of school, maybe the second week of school, where we were talking about independent and dependent quantities in just a sentence, in like a word problem. If you remember, I think what we did was we circled the independent. I like to use the color blue. I don't know. It feels like blue is more independent than red, which is what we're going to underline. Really, here, all I'm asking you is write it out. So in this case, you don't have to follow that sort of pattern of circling and underlining, but we're just going to write out the independent and dependent quantities in each of the problems. These ones are nice because generally you're going to find a quantity when you see number. Right? Number and then something, or amount, right? Those are quantities. Those are measurable things. So let's go ahead and think about it. The most helpful sort of sentence starter or like way to think about these problems is to use this as a framework. Okay? And in order to answer these problems, this is what you need to ask yourself in your head. You're going to start off with one of your quantities. I'll just leave it blank. So blank, and then you're going to say depends on blank, which would be your other quantity. Now, the dependent quantity is the one that depends, right? The dependent quantity depends on the independent quantity. Very often in our classes, we're going to see things like time be an independent quantity because time doesn't really depend on anything, right? Time just moves forward no matter what we do. Whereas, things like our position or like our height above the ground or our distance from school, those things can change based on how long we've been driving. In this scenario, all we're going to have to do is look at both of our quantities and figure out which way it works, which one depends on which, and whether or not that makes sense. Okay, so let's read this first problem. We have our two quantities here. I'm going to highlight them. The first one is the number of times that you take notes in class and the number of times that you sharpen your pencils. Now, these are related. I mean, hypothetically, right? Maybe not everyone takes note in pencil, and maybe you have a mechanical pencil. I don't know. But, just pretend for a second we're using Ticonderogas. We have to think about which one of these things depends on the other. And so I'm going to read both in my head and figure out which one makes more sense. So let's start with this. Let's say, just hypothetically, the number of times you take notes in class depends on the number of times you sharpen your pencils. Let me repeat that. The number of times that you take notes in class depends on the number of times that you sharpen your pencils. Now, as a teacher, I often make my students take notes. I have never once kept track of the amount of times that someone sharpens their pencil. So I'm not asking my students, hey, have you sharpened your pencil 5 times today? Because if so, then we're going to take notes, right? That's not how it works. The amount of times that you take notes kind of just happens on its own, right? And in fact, it happens first. You have to take notes and then you sharpen your pencil because it's dull afterwards. Well, unless you buy an unsharp pencil. But in this case, I think it works the other way around, meaning this. I think that the number of times you sharpen your pencil, and I didn't give you enough space to write it out entirely. So let's say sharpen pencil, that second quantity, that depends on the amount of time you take notes, right? The more I take notes, the more times I have to sharpen my pencil. Not vice versa. If I sharpen my pencil 100 times, that might have no bearing on how many notes I would then have to take. If that makes sense. Okay, let's keep going with the next one. Here's the next sentence. Our two quantities are your grade on a test and how much studying you do. Ooh, interesting. Let's think. All right, let's read it like this. Your grade on a test depends on how much studying you do. Your grade on a test depends on how much studying you do. I mean, right away, I think that makes sense to me. Like, the more you study, the better your grade is, right? Generally, or at least the amount of studying you do would affect your grade on a test. Vice versa, right? It's not like you know what you're going to get on the test before you study, right? It's not like we hand out our grades to people and then assign how much the studying they should do. I mean, assuming this is for the same test, I guess your grade on a previous test might impact your studying in the future, but assuming this is for the same test happening at the same time, I would say that the way I said it first, your grade on a test depending on the studying you do, that makes sense to me. So I would say your grade depends on how much you study, right? How much studying. Okay, how about this? We have the amount of hours that you work and the amount of money that you make. Once again, I'm assuming like the amount of money you make in a day. Well, this one's not too bad either, right? If I work for 8 hours in a day, I'm going to make more money than someone who's working part-time or 4 hours a day or 2 hours a day, right? And so I would say that the amount of money you make depends on the amount of hours you work. Amount of money depends on the amount of hours. And once again, this is an example of where we have time as our independent scenario, right? The amount of hours that you're going to do, often that's decided for you as working, and then what changes is the amount of money that you make. Okay. So here we go. There are the three answers for here. I think sometimes in some of these scenarios, you can argue the other way. And if you feel comfortable writing out why you think an answer is the way that it is, then I'm all ears, right? But what that would mean, like graphically, is switching the x and y axis, which works for some functions, doesn't work for others, right? So some of these scenarios are going to be pretty cut and dry. Some of them might be open to interpretation. But here we go. There's number one. So let's head on to number two. All right. This one is a word problem, and it asks three things of us. Okay, we're going to have to read this word problem, and then we're going to have to figure out independent and dependent quantities. We're going to have to figure out where this graph is increasing, decreasing, or constant. And then we have to figure out domain and range of this scenario. Okay, so let's break it down. Let's read the question first. I think that's always a good place to start. Sam rode in a hot air balloon. After the balloon began its initial descent, so he's already been riding for a while, but now it's heading down. It's on its ways down. It stayed in the air at a constant height for a while and then continued its descent towards the ground. The graph shown represents this situation. Okay, here's the graph. So we have him starting, at 0 minutes, and then he's starting his initial descent, and he's heading down. He's up here and whatever how high up the ground, and then he's heading down, and then it stayed in the air at a constant height for a while. That's going to be right here, right? Time is moving forward, but our height stays the same. And then he continued his descent towards the ground, which is right here. Okay. Now, you might have to, like sometimes, and this is like kind of the first thing we did where we matched the graphs to the scenarios, the independent and dependent quantity, you kind of had to read into the question. But if I give you the graph, there's actually a really fast shortcut. And it's just remembering that the independent quantity is what we put on the x-axis, right? The way I like to think about it as well is, and this is a good example, we have time here as our independent quantity, and it's time in minutes, I guess. But, if you were to think about time time always moves forward, right? We can't ever stop time from moving forward. And so I think it makes sense to go on the x-axis, always moving forward. Okay. And if the independent quantity is on the x-axis, well, that means that the dependent quantity is going to be on the y. And that makes sense too. It's our output, right? It's the thing that's changing. And so our height from the ground is going to be the dependent quantity. And I guess that's in feet, which, use that whatever you will. Okay. Now the second part, we're going to label the sections of the graph where SAM is increasing, decreasing, or constant. Okay, the thing you have to remember for this, the rule for figuring out increasing, decreasing, constant, is you always got to remember we got to read left to right. Oh, I skipped the word. Read. I have to rewrite it. Read left to right. So we have to start when x is smaller, and then we have to make x bigger. And that's how we look over time, right? From 0 minutes to 50 minutes in this case. That's how we're going to read it. And that's the case for every graph, okay? And so basically, one thing I like to do is pretend we have a little ant on this hill, or some sort of, creature that would be walking along our slope. And he's always going to be moving from left to right. Is he heading up a hill or down a hill, right? Is he heading higher in the y or lower in the y? And in this case, as x goes forward, our y gets lower for this first section. And so how I would label this is I would just draw an arrow here. You could say like a little minus sign in parentheses, or you could just write decreasing. I think that's a great thing to label it. Okay. Then for his middle section, the hot air balloon stays at a constant height for a while, which this word constant, well, that's going to help us out with this. And really, I mean, we can visually see it as well. As time moves forward, our y is actually going to stay the same. Our height doesn't change. And so at this rate, I would just write it's constant. I don't know if a good symbol for that, maybe just a blank parentheses, maybe a 0 in there. I don't know. I don't know if there's a traditionally used symbol for that type of thing, but I would just label it as constant. Okay. And then in this last section, he descends again. Well, descent is going to give us a little bit of a hint as well to what he's doing, but we can double check as time moves forward. As we move left to right on the x, he is heading down. So we're going to go ahead and say this is also decreasing. I guess Sam doesn't have to be a he. But anyway, Sam. Okay, last but not least, we have to identify the domain and range. Okay, it seems like a lot, but really, this is sort of just an analysis of graphs, making sure you can read what's going on in this scenario and remembering what each part of this question really is asking. And so for the domain, here's how I like to define the domain. It can be one of like 3 things. I mean, it's really all of them at the same time, but the domain is all possible x values, okay? What are the things, if we're looking left to right on the graph, where does our curve or our set of lines exist, right? That's the domain. Alternatively, it's all possible inputs. Okay, and remember inputs are kind of interchangeable with x values at this point, which is also just the independent quantity. Like it's how much independent quantity, sort of the range of values, well, range is a bad word, the set of values that exist within our independent quantity, which in this case is time. And so here's how I would read this. I'm going to start on the left-hand side and move to the right. You don't have to for domain, but I mean, it just makes sense to keep reading left to right. And I'm going to look for where my graph exists. Okay, and what I mean by that is, where does this curve, this representation of Sam going down in the hot air balloon exist? Sorry, I had to erase the ant so we could see. Well, it starts at time 0, right? When I'm at 0, that means I just started my graph. Okay, and I don't have arrows on my graph, keep in mind. So, I mean, I drew some here, but that was just sort of signify the direction it was going. However, in this actual scenario, we have a beginning point and we have an endpoint. Okay. And so what we're going to do is identify those beginning and end points in terms of x and y, and that's going to be our domain and range. So here we go. Our first point where our graph exists is at 0. And so in the domain, the lowest value is 0. And then it goes all the way up until we reach here where our graph stops at 50. Okay. So I'm looking for every place my line exists, and it exists between 0 and 50. So you could write 0 to 50 if you would like. A more technical way that you could do it would be this. 0 is less than or equal to, right? Because we can't include 0, x, right? All our x values, which are less than or equal to 50, right? All of our x values, all of our domain exists between 0 and 50. Okay. Well, range is similar, except instead of looking left to right, we're going to look up and down. Okay. We're going to look top to bottom or bottom to top. So the range, by definition, is this. It's all possible y values. Which, if it's all possible y values, it's all possible outputs. Or it's where our dependent quantity exists. Dependent. D-E-N-T. I think that's how you spell it. I don't know. We could ask Malcolm more, I guess. Quantity. Anyway, we're going to look from the lowest point that our graph exists all the way to the highest point that our graph exists. Okay. Well, thinking about it in the scenario, his lowest point is the ground, right? His lowest point is being 0 feet off of the ground. And so it's also 0 to something else. Well, what's his highest point that he's ever in the air? Well, when he started his descent, that was when he was at his highest. It's in between 2,000 and 2,500. The number for that is 2250. Okay, 2,000. Oh my gosh, what am I hitting? 2,250. And so one way you could write this would be 2,250. The very mathematical technical way, and this is the way that Mathia likes it, so I like to show it, is 0. Oops, let me rewrite that. 0 is less than or equal to all of our y values, which are less than or equal to 2,250, right? All of our y values exist between 0 and 2,250. Basically the same way of writing these. Range just implies that it's all possible y values, and so the y's exist between 0 and 2,250, this part of our graph, right? Because we have a graph all the way there. If our graph extended upwards past this point, then we would change the range. If we somehow went into the ground, extreme hot air balloon accident, then we would change this range as well. But based on what we have, this is what we're looking at. Okay, kind of a long problem, but really it's just sort of understanding what it's asking at each section. And so I would practice this on the right-hand side. You have a similar looking problem, just with different numbers and a little bit different, increasing, decreasing scenarios as well. So give this a try. Try to write the domain in this fancy fashion. It's going to help you out in the future. But really what it's saying is 0 to 2250 and 0 to 50. And you're looking for x in the domain and y in the range. All right, let's move on. Here's question 3. This is one that's going to be super similar. You're going to see it on the test. The right-hand side of this problem is a little bit of an extension. So what you're going to do on the right-hand side is use these sort of word problems to label the graphs, right? An independent and a dependent quantity for each. But for this problem right here, all we're going to do is basically try to match up. I don't know if this is the right answer, but we're going to match up the correct scenarios to the correct graphs. Okay, so let's read through all 3. The first one is called test score, and it says Arlene begins a test with a possible of total of 80 points. She loses 2 points for every question she answers incorrectly. Okay, so when I'm looking through this, I'm going to look for some keywords that are going to tell me the direction of this graph, or potentially how this graph is going to behave. And the first thing that I notice is it says loses, right? And when I think about losing, I think about going down, right? If you lose a bunch of games, like if the Mariners lose the rest of their games for this season, they're going to go down in the standings. That was a knock on wood. Well, I hope they don't lose. Anyway, and so, I mean, kind of right away, I can see that this graph should probably be decreasing over time, right? It should start up higher with a possible total of 80 points. And then if you get questions wrong, you lose points linearly, which is going to be graph 3, right? Right away, I mean, I can just notice this is the only graph that heads down. We have to read left to right. And so as x increases, y decreases. This is going to be our test score. Here's would be our 80 points. And then each time we lose a point or miss a question, we lose some points going down. Okay. And notably, it doesn't have an arrow because you can't get less than 0. Well, at least I haven't yet on a test. Don't try to. So this one is graph A, or situation A goes to graph 3. I don't know what I did there. Anyway, so we got 2 left, B and C between 1 and 2. Okay, next one's piggy bank. He has 10 pennies in his piggy bank initially. He doubles the number of pennies in his piggy bank each day for 5 days. All right. Well, I see a very special word. Kind of like loses. I mean, we have something here, doubles. Doubles is a very, very interesting word. And it implies, when you hear the word double, it definitely implies exponential, right? You think about doubling your money, tripling your money. That is exponential growth. It is greater than just taking in away and adding and subtracting. You are now multiplying things, okay? Which is then going to tell you we are now growing at a faster rate than a straight line, okay? And very often, in fact, our whole exponential unit in this class is framed around money and finance. And so when we talk about money problems, very often we will be using exponential equations. So that's a good hint. And graph 1 is scenario B, okay? Which leaves C to graph 2. If this was the SAT, I would mark it as done, go to the next page, right? Stop wasting time. But for this, let's just go ahead and double check, make sure we didn't mess anything up. There's a potential I read a question wrong, it's happened before. And so let's just read this. It costs $5 to enter the school's fall festival and around 50 cents per ticket purchased. Well, if we were thinking about the total cost, right, how much it would cost me to go to the school's fall festival, right away at the very beginning, it would cost me $5. So I'm not at 0, I'm immediately at 5. And then every time I purchase a ticket, my total cost is going to go up linearly, right? I'm purchasing 50 cents at a time. I'm not doubling the amount of cost. I'm just chalking another 50-cent ticket, right? I really want that giant stuffed minion. And so I'm going to keep playing the ring toss into the bottle until I get it. And then I'm going to be way over here. And notice this arrow goes on forever because I do suck at the ring toss game. I will spend all of my money trying to get the giant stuffed minion. So there we go. B, C, A. I don't know why they're different colors, but that's okay. All right, question 3, done. You're going to read them. On the right-hand side now that you know which scenario goes to which, go ahead and match up. Figure out what would you label the x-axis as, what would you label the y-axis as, okay, using the text, sort of the clues in each of these prompts. All right. Number 4, here we go. This one's super fun. We have to determine whether each relationship represents a function. I had to think about, we get to look at people's relationships and determine if they're functional, but except they're not people, they're numbers. So you don't have to feel bad if they're not functional because numbers don't have feelings. All right. And then we have to explain why or why not. Well, explaining why or why not, actually not too bad in this one because if you can determine whether it is a function or not, then you have your logic there. Okay. The first 2 we have are graphs. And the thing I want to talk about with graphs is a specific test called the vertical line test. Okay, the vertical line test. And here's how it goes. If I can look and find a spot on a graph where drawing a vertical line would cross my graph more than once, then I know it's not a function. Okay, so a vertical line can only cross the graph one time. Okay, when I mean graph, I'm meaning like my curve, whatever's curvy, or my set of lines, whatever's plotted on my page. So one thing I like to do is like sort of recolor my lines so that I can visually see the vertical line. I'm not talking about the axes. I'm not talking about, any of the sort of boundary markers. It's just whatever I've plotted. Okay, a vertical line can only pass through it a maximum of one time. In other words, if a graph ever loops over itself, then you know it's not a function. And the reason for that, because the definition of a function is this. Here's the definition of a function, which is also important for this page, and especially for these two. Simply put, it's this. Every input, right? And remember, input is our x values or our domain. Every element in the domain or every input has exactly one output, okay? Which is like a y value or an element in the range, okay? Every input, every input x has one output y, okay? So back to the graph example, and I'm going to start with B because this one's a bad boy. I'll just give you a little spoiler. If I try to draw a vertical line across my graph, I'm going to notice that right here, that's a bad color for it. I'll do it in blue. Right here and right here, at this one specific x value, right, at x equals 2 or whatever this is, there are 2 times that I have an output. Right, something in my y. I have 2 y's right here and right here for 1x. That breaks the rule of a function, right? This is a single input with 2 outputs. And that would be my explain why or why not. You could say 2 things. It fails the vertical line test. You could say, no, it's not a function. It fails the vertical line test. It has 2 outputs. What the heck am I doing? 2 outputs for 1 input. Okay. So this is not a function. And in fact, anywhere you draw these lines past here, it'll work. And you only have to find one spot. You only have to find one bad spot to ruin the entire thing, make it not a function. Okay. So on the contrary, let's look at this one, right? This is an exponential. It's heading out infinitely towards the left and heading infinitely up and to the right. And visually, I guess we just have to think about, does this graph ever loop over itself? Is it ever going to cross back over? And I don't think so, right? If I draw this vertical line right here, that's a really bad vertical line. Let me try again. Oops. If I draw this vertical line like right here, I only cross my graph one time, right there. If I draw my vertical graph or vertical line right here, I'm only ever going to cross it right here. And so this, in fact, is a function, yes. And it passes the vertical line test. That's one thing you could say. It passes vertical line test. And you could say every input has exactly one output. Cool. So for graphs, the vertical line test, super helpful. Okay. Now for these two, the mapping, sort of ovals and the table, it's not as helpful, right? We can't draw vertical lines here. We have nothing graphed and plotted. So instead, we just have to use some of our logic and figure out inputs to outputs, okay? So remember, inputs, that's what we're scanning for x. So x is going to be our inputs, and domain in this case is going to be our x, which is also our inputs. Okay. Now, this one right here, I like D a little bit better to start with. And we have something interesting going on, okay? Now, if you take a look, each element in the domain, each x value has one arrow stemming from it, okay, and heading towards either -1 or 1. Now, if it helps, honestly, don't care about the numbers. The numbers really don't matter. It's just kind of thinking about inputs and outputs and how many times an input has an output, okay? And so even though this 2, which then has an arrow connected to -1, this 2 maps to -1, so does this 3, it maps to -1, but that actually doesn't break the rule because every input, like this input 2, has exactly one output, which is -1. This input 3 has exactly one output, -1. And this input 4 has exactly one output, which is +1, right? And so even though the output is the same for these two inputs, it doesn't break the rule. Every input has one output. Okay, so this one is a function. What's funny is like explain why or why not. If you were like in a like a proof math class, you could say by definition, but in this case, you would say every input has one output. Every input or element of the domain has one output. Okay. So now the table. And the table I think is the trickiest. And it's also the place that I'm going to try and trick you, if I'm being honest. Okay. Because tables can look so good. Everything can be perfect until one little mishap, one little repeat. Okay. However, this one, I think maybe we could figure it out. So here we go. Remember, every input has to have one output. And so I'm going to quickly just scan through all my inputs that I have. The first one here is a -2. And if I look at my next value, it's actually also a -2. Okay. Now that's legal, right? You can have more than one entry with the same x value in a table. That's fine. But in order for it to be a function, that the corresponding y value, the y value that goes with the input, has to be the same every time, right? This 2 can only ever go to one y value. That's just the definition of a function. And so when I look at this table, I see that this 2 goes to 100, or -2 goes to 100, and also at the same time, -2 goes to 50, right? Which is kind of like if I drew it like this, I drew it like the mapping example, that would mean there would be 2 arrows. Oh, that's not a good representation. The bottom one's got to go, or the top one's got to go to the bottom. This -2 also goes to 50, right? -2 is the same as -2. Doesn't matter that they're in different rows. It's the same input. And they go to 2 different numbers. So that breaks the rule. That's a no, right? One quick way to check, if there's ever more than one arrow stemming from an input or a domain element, then it can't be a function, right? And that happens here, right? If I drew these arrows out. -2 goes to 100. -2 also goes to 50. So the input -2 has 2. Let me write it not as a number. That would be confusing. Oh, cool. Now I have to rewrite it all. Input -2 has 2 outputs. That is illegal because 2 is more than 1, right? It can only ever have a 1. And even though these other 2 are okay, 0 going to 0 and 2 go to 50, that's fine. It just takes one bad example to break the whole function, or non-function in this case. All right, this is super important, figuring out if stuff is a function or not. You have to use this definition and sort of this is how you're going to explain it. So I would write this down as notes on your sheet as you work through it. There's another example on the other side for you to figure out as well, okay, where you have to sort of draw your own. So you have to make something that is a function and not a function. And so you got to use a little bit of creativity. You can make it as complicated or as simple as you want, okay? So try that out. Here we go. Last question, number 5. Sorry, it's a little blurry. This is a big like section. I wanted to make sure you could see the graphs. But really what we're going to do here is match each function to its graph and explain our reasoning, okay? This is really important. This is like basically what we did with the sort of sorting example that we've been doing the past couple of days, as well as that example where we would look at a bunch of graphs and figure out which sort of type of equation could go to those graphs, okay? And sort of defining each different type. So I'm going to go through that. I'm going to talk about the 4 major function families that we're going to use on this type of problem, okay? And it's also going to be our 4 major units in this class. So here we go. The first type of function family is linear, right? And the cool thing about linear is that it's made up of lines, right? It's linear. And so anytime you see a straight line, it can be in either direction. It can go up like this, it can go down like this. As long as it's just one straight line, it is linear. And you will often see it like f of x equals x, or you would see it as 2x, or you could see it as 2x plus 1, right? These are all linear functions. And in fact, the standard form for it is ax plus b is what we use. You might have ever seen y equals mx plus b as well. That is a linear function on its basic level, okay? The most basic one I can think of, though, is f of x equals x. Now, honestly, it's kind of hard to figure out linear functions sometimes if you don't know the other rules, because there's kind of nothing weird with it, right? And there's no like hard and fast way to figure out, like if it just has an x, I guess is one way to figure out if it's linear. But right away I can see that graph D is my linear graph, right? It's a straight line, okay? And so now I have to think about which one of these, A, B, C, or D, represents a linear function, okay? Well, as I scan through the rest, I have to find something that looks something like this, right? This A and B could be numbers, or M and B or whatever. Or this could be alone, or it could be added to something. Who knows? So I'm going to look through the rest of my equation and spot dissimilarity, something that's weird with them, okay? So in A, when I spot it, well, I see that there's like this weird 2 up top up here. Sort of covered it up, actually, so sorry. There's a square, right? It's negative x squared. My linear function doesn't have that. So I don't think this can be linear. This one right here, if you can read it, is 2 to the power x, meaning the x, our variable, is in the exponent of a number. That is weird. That's not like this either. Okay. So if I go to C, this one's also kind of close. I mean, there's an x minus 1, but that could be linear. However, there's these 2 bars, and we'll talk about what those mean in a minute. And I don't see any bars or any sort of thing like that in this equation, which means that it's got to be D, which is just x plus 1. And really, a good sort of mental shortcut to take is if it's the simplest looking equation, then it's probably linear. And so this one goes to graph D. So I would put next to my graph, or on top of my graph, D, because this one is D. Okay, so we have that one done. So I'm going to cross it out. The next type of function family we have is exponential. Okay, now we had an exponential example earlier with the money. Here's a simple example of what exponential looks like. It's going to be something like that, where that's actually kind of bad. Let me redraw it. Let me try again. Like this. It sort of ramps up. Alternatively, right, it doesn't have to head up in that direction. It could exponentially decay like this. It could also be flipped around, right? It could be something like this. Oh wait, that's the same thing I just drew. What would be the other example? Like this, I guess. That could also be exponential, right? Anything that looks like this sort of one-sided sort of ramp-like curve, like the Ninja Warrior wall, if that helps, or, you know, it's not symmetrical. It's super, super steep at some points, and then it flattens out on the other side. You're going to know that's exponential, okay? And that's graph B in this case. Now, the equation, the function for exponential, the most important thing that happens is that there's some number on the bottom. Now, it can be any number, 2, 3, 4, whatever you want, as long as it's bigger than 1, or not equal to 1, actually. And the most important thing is that there's an x in the exponent, right? It becomes exponential if x is in the exponent. And so if the variable x is in the exponent, then it's going to be exponential, okay? And so when I look at my 4 different graphs here, we recognized that earlier. It was this one. I have an x, my variable, in the exponent. And so I got to see that graph B, or sorry, equation B goes to graph B. Oh gosh, hopefully it doesn't just follow this pattern entirely. Okay. The next function family we're going to talk about is quadratic. Quadratic, okay? Now, we've talked about quadratics a bit. The key thing with quadratics, if you're going to look at it visually, is that they are represented by what are called parabolas, right? This U shape. Right? We call these parabolas. Quadratic functions are represented by parabolas, and parabolas can be all over the place, right? They don't have to be up like this. I mean, they can open up like a cup like this, or they can open down like a frown right here, right? And they can be shifted around, they can be moved up, down, wherever you want to go, okay? The only important thing is that it's curvy, it's symmetrical, it sort of extends out in both directions, and it's got this sort of lowest or highest point, the vertex, right? Really, it's got this U shape. So when I look at my remaining 2 graphs between graph A and graph C, well, this is maybe a it's got a minimum point, it sort of bounces back up, but it's definitely not curvy, right? Whereas graph A is. So this is going to be our parabola. This is going to be our quadratic function. And so we just have to match it to which equation? Well, for quadratics, the most important thing, and this is what we're going to see, when you have a quadratic equation, somewhere in there is going to be an x squared. Now, we're going to get it later on, and we're going to write quadratics indifferently, but for right now, you see that x squared, just know that's got to be quadratic, okay? So you're looking for x squared. You're looking for x squared to make something parabola or quadratic. And so when I go back up to my last 2 remaining answers right here and right here, I guess I can cross this one off. We already have it. Only one of these has an x squared, and it's equation A, right? You have that x squared right here. There's an x on the base. It is raised to the power 2. That's going to signify that my graph, when I plot it, is going to be a parabola. And so this is going to be equation A. Nice. All right. Which, if we know those 3 things, then we could figure out the last one just by process of elimination. It is going to be C. Let's go and explain why. Okay, let's explain why. And so the last function we have is called linear absolute value. Okay, and this is a whole unit that we have. And these graphs are going to be represented by these sort of pointy V shapes. Okay, something like that. Or they could be upside down and like this as well. Okay, but they're straight lines, as bad as I can draw them, I guess. They are straight lines, and they come together at a point and then bounce off in the basically same slope, but in the other direction, right? So whenever you see a V shape like this on a graph, you should be thinking V for value, right? V for value, V for absolute value. And here's what it looks like as a function, okay? Well, in the other ones, we found what was different. For quadratic, it's got to have a squared. For an exponential, it's got to have an x in the exponent. I mean, it's kind of in the name here. For it to be an absolute value, it has to have the absolute value signs, which are these 2 bars like this, okay? We represent absolute value as 2 bars with numbers in between them, okay? Now, what absolute value does mathematically is it takes numbers and it figures out how far away they are from 0, right? We can't really conceptualize negative numbers in real life, and so we think about negative numbers as their value. And so this -5, well, it is still 5 away from 0. And so if I take the absolute value of -5, it equals 5. A common misconception is to think that absolute value switches the signs. It makes negatives positives. That is true, but the absolute value of +5 is also 5. So it keeps positives the same. We'll get into absolute values and what they mean and solving equations with them and all that later on. in the year. But for right now, graphically, what you're looking for is a V shape. And in the equation, you're looking for the absolute value signs, which are these two bars, okay? And so we have it right here, which does relate to graph C, or graph A. Equation C goes with graph A. All right, and that is it, okay? I recommend if you're gonna do the right sign, which you 100% should, as well as take notes on this, write down all this stuff, right? Keep this as notes. If you're in my class, at least, if you complete the left side, follow along with me, which you just did, congratulations, and the right side on your own, you may use it as notes in the test, right? And that's just a really good security to have. I mean, you've done all this pre-work, you've done all this studying. I'm sure you won't need it that much, but it just feels good to have these notes to double check them, okay? So thank you for spending this time with me. Thank you for following along. What I'd like you to do now, take those problems on the right-hand side and try them, right? Try them the best that you can on your own. And if you still feel stuck, go back to this video, go to the section where the problem is talking about it, and rewatch what I say, rewatch how I explain it. But that's going to be it. Thank you for watching the Module 1 Topic 1 review. And best of luck on your test. You're going to crush it. I mean, if you got this far, there's no stopping you. All right. See ya.